And our first team is Team 11 on UAV collision avoidance. The customer for this, and we are happy to have a variety of faculty, industry, and other customers. The customer for this project is Dr. Kenn Sebesta, who's a postdoc here at Boston University. So without further ado, this is Team 11, UAV collision avoidance.
Hello all, good morning. My name is Jim Lee and this is Team 11, UAV collision avoidance. We're composed of William Anthony, Alexander Tooke, Besmir Sulejmani, and Kenn Q. So last semester we were given the problem of creating a reliable collision avoidance system with UAVs interacting in a swarm using ultrasound that is emitted from their motors. So the UAVs that we are using are quadcopters, and each of them has 4 BLDC motors, brushless DC motors. So the ultrasound emitted from that is just a frequency that's generated from the motors. And we're able to manipulate and control this to create a UAV collision avoidance system. This system is supposed to be designed to passively detect, identify other UAVs in the form, and also locate the position of the UAVs. So moving on to the relevance and the purpose of this project, it's mostly for scientific research. Each UAV can be seen as a node on a mesh network so that we can really identify each individual UAV and see how they're working together as a group and as a swarm. This method is also cheaper to manufacture, so it's very cost efficient and deploy in regards to other piloted vehicles. And the passive sensing system just generates less operating costs in general. So this project concentrated on 3 areas. We began first with detection. So we wanted to create a mechanism in which we could read in the signals being generated by the BLDC motor. And since the presence of the quadcopters, we did a lot of testing. We found a way to read in the signals and show it up on MATLAB, and we were able to complete this first semester. Next, for this semester, we moved on to 2 other stages. We moved on to identification and positioning. Identification, we were able to differentiate between different signatures, different sound sources, and identify which quadcopter or motor was being displayed, what frequency it was emitting. So we were able to manipulate the algorithm in that way to identify individual unique signatures of quadcopters. The other part of our project involved positioning, in which we were able to use time delay of arrival of the frequencies into the microphones and create an algorithm that would utilize multilateration to find and position each of the quadcopters. So the entire phase and the entire process of our project can be pretty much summed up into this block diagram. We begin with the user input, where a user defines which frequency he wants to emit. So we have basically 2 frequencies that are emitted that switch on and off, that we can correspond to a bit stream that identifies each individual quadcopter, and the user inputs this, so this is user controlled. And this goes into a computer with ECE control. We have a MATLAB program that is able to control the BLDC motor using the process. So that entire first block we have there is the first part of the process, where we can control the motor and emit specific frequencies. That took us, the first beginning half of this semester to do, and we were able to progress from that. Moving on from that entire section, we look at the amplification array. So we were able to develop an amplification array using a circuit that was able to amplify the signal coming in that was emitted by the BLDC motor and process it through a sound card. So this step was completed last semester, and we were able to get pretty good results with it. Moving on, we have our next big block. After the application array, we move on to the sound card and then into the port audio I/O, which was a program that we found that was able to read through each of the signals and process and allow us to see, manipulate, and really play around with everything. The two main parts of our project was basically creating a positioning identification algorithm, as I described before, and this was all done through MATLAB, so we were able to complete this. The end result of the project, the end result, what you would see is a user interface. So in the case of our positioning algorithm, we output a GUI, graphical user interface, or in the case of our identification, just the ability to see the binary stream that was sent in and that was received. We'll go into that later in detail. So fall semester, we began, and I said we received the problem, we received our project, and we spent a lot of time researching, identifying what we would do, how we would go about accomplishing our goal. So our first step was to find out a way which we could read in the signatures that are coming out, the frequencies that are coming out of the BLDC motor. We did that by creating a preamplifier circuit. You see on the top right is the circuit that we use just to amplify one microphone. We have actually 4 microphones on our actual circuit, so this is just one of them displayed in a circuit form. What we have here is that we input a low voltage, so low voltage audio signal from the microphone. So when we emit the signature, it is processed through this microphone. This circuit amplifies that voltage so that we have a gain of 200, so it can be read through the sound card and processed. The electric signal read in by the sound card into the computer is then read into the next part, the MATLAB program, which we also designed fall semester. You can see the results of one of our tests to the bottom. That was just some random noise in the senior design room that we had. The random spike that you see is just one signature. We emitted a frequency so that it could be seen by this microphone array slash MATLAB program, so that we could see that it was receiving some signal. So that random pulse that you see is just one of the things being generated by a random iPhone application that we found. So we were able to get pretty good results from the beginning. So this was able to read in, and we were able to play around with a lot of the different techniques that we were going to inevitably use to create our positioning identification algorithm. Over here, I just wanted to show what our actual circuit ended up looking like. This is just a display of it. You can see the 4 individual microphones and then the op-amp that's amplifying them.
So entering into the spring semester, what we were able to do was we had the live audio coming in through the audio card and being processed through MATLAB. Now that we had this done, we had to change the pulse width modulation frequency of the BLDC motor that would be able to give us the bit stream that we were going to detect. This was done, as you can see, the electronic speed control, the ESC, down the bottom. That is interfaced through a USB to serial port, which connects to the computer, and then you can send serial commands to the ESC. And then this is able to change the pulse width modulation of the frequency of the motor, which is what changes or emits the sound that's picked up through the microphones. We were able to do that pretty effortlessly. The ESC was provided to us by our customer. It's part of the open pilot program because most ESCs emit only just one frequency, so we were able to get that varying frequency that can give us the bit stream. After we got that bit stream into the computer, we did some signal filtering. We used the Butterworth filter to separate the different frequencies that we were looking for. And then, so we were able to get the frequencies, and the way we encoded the bit stream was using audio frequency shift keying. Basically, I'll go into this a little bit more in detail, but the ones is calculated as one frequency and the zeros emitted as another frequency, and that's emitted through the motor. So it's just changing the frequency of the motor. And then finally, we were able to calculate the position of a noise source. This is done through the time delay of arrival to the different microphones, and I will also get into that later. So going into frequency shift keying, as I said earlier, it's basically modulating your bit stream of ones and zeros into two different audio frequencies. This picture shows pretty well that you have one frequency set as your ones and another frequency set as your zeros, and so you change the frequency, the pulse width modulation frequency of the motor in order to send that bit stream. In order to demodulate it, it's done through this this block diagram. So the modulated audio is going into this, which is done, all this processing is done in MATLAB. The audio goes through two bandpass filters, one that is detecting the one frequency and the other one that's detecting the zero frequency. And then we pass that through an envelope detector, and then we do this, we subtract the zeros from the ones to give us a better spread, and then we can sample it to get a bit detection. And then, as I said, we were able to do the positioning calculation. This is done through time delay of arrival. Basically, when you have two signals and one's delayed by another one, the cross correlation is going to give you the time that that delay is, what correlates best to it. So we took the cross correlation between microphones 1, 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, and 3 and 4. So there's 6 different cross correlations that we're able to determine. And then we took the peak of these cross correlations and we using the speed of sound and algebra, able to find the position of the sound source.
So here's a little bit more about the cross correlation. You can see the first line is just the definition in the time domain. Basically represents a shifted version of one signal passing over the other one and multiplied. So what that ends up giving you is the maximum of that cross correlation function is the most likely time delay in samples. So the time domain implementation is actually pretty slow. It's about n squared runtime and doesn't allow for easy filtering because you have to send pre-filtered data into the function. So what we did instead is implement it in the frequency domain, which you can see the definition here, the second line. So basically this allows us to do it with much faster runtime, about n log n, rather than n squared. So you can have a speed up of 10 to 100 times depending on the length of the signal you're processing. And it also allows us to easily weight different frequency components. In our case, what we did was weight the frequencies emitted by the motors equally and toss out everything else, basically. So we don't have any low frequency noise. We don't have any high frequency noise. We just are looking at the signal from the motor and finding that correlation. And then you just take the inverse transform to get that back into the time domain. And I'll show you a sample of it now. Basically, what this is just a signal from one microphone, and it's ideally time shifted some certain amount. And the second picture is just the cross correlation function from the frequency domain implementation that we wrote. You can see that sharp peak, which corresponds to the time, which you can relate back to the time delay in samples, which then you can divide out the sampling frequency to get the time delay in seconds. So this is the basis for calculating position from an array of microphones, which I'll go into a little bit how that works. So basically, we calculate each of the 6 cross correlations, as you heard earlier. Actually, only 3 are needed for the calculation, but what the 6 different ones gives us is they should satisfy phase closure. That is, the 3 extra time delays can be written in terms of the first 3. So I gave an example here, T1 to 4, which is the time delay between mic 1 to 4, and subtract T1 to 3, and you should get T4 to 3. So what we can do is check each of those phase closure equations and make sure that they're satisfied, and if they're not, we know that we're wrong. So we check each of 4 peaks for each correlation, and we just loop through them until we find one that works within some small margin of error. and then we send the vector of time delays back to the position calculation function, which is actually a pretty simple idea. It's just based on the 3D distance formula. Here, dSi is the distance between some noise source S and microphone I, where I is 1, 2, 3, or 4. And the idea is that we can write the distance as the speed of sound times the time that it took that sound to travel between the source and microphone I. And then we subtract any two of these equations. As I just gave an example, ds1 minus ds2, and you just get these square roots subtracted, and you can then write the distance as continued. The speed of sound, Vs, times the time it took the sound to travel between the source in 1 and the source in 2. And that subtraction, Ts1 minus Ts2, is actually the time delay between microphones 1 and 2, which is what we get from our cross-correlation function between the signal at microphones 1 and 2. So what we end up with is a system of 3 equations with 3 unknowns. Say we can have the time delay between 1 and 2, 1 and 3, and 1 and 4. And then, of course, as I said earlier, we also check that against the time delay between 2 and 3, 2 and 4, and 3 and 4 to make sure that our time delays are correct. And so the 3 unknowns are x sub s, y sub s, z sub s, where those are the 3D coordinates of the sound source, and each of the x sub I, y sub I, z sub I are known because we obviously can measure where we place our microphones. Using a whole lot of algebra, basically, we simplify the 3 subtracted formulas to a quadratic in z sub s and 2 other equations in x sub s and y sub s, and program the computer to solve those equations as the time delays come in. A little bit about the accuracy. It depends on a whole lot of factors. Sampling rate is one, that the higher the better, basically, because the finer the resolution you get in delay in samples. Microphone placement plays a big role. What we do now is we just have one microphone at like an origin of an XYZ plane, one on the x-axis at about 2/3 of a meter, one on the y-axis, and one on the z-axis at the same distance. Potentially we could find a better arrangement, but this seemed to work pretty well in simulations. The sound quality of the microphones plays a big role. Obviously the better it is, the better the cross-correlation you'll get, cross-correlation quality. And the actual position of the source, which is again related to the position of the microphones. There are certain zones where the accuracy is pretty good, like within a couple centimeters, and there are some zones where we have maybe half a meter spread, like along the axes, don't work so well, but okay.
So over here is a picture of our microphone array connected to the sound card. And this is the zoom in of the microphone in one of the coordinates in the pyramid. This slide, the image over here is the position calculated from a noise source, which was an iPhone app, and on a 2D plane. So with all the accomplishments we have so far, further work on the subject would involve integrating all the components together and mounting them in a quadcopter. Our algorithms on positioning and identification would then be ported on the microcontroller. In addition, instead of using the BLDC motors to emit sound for detection, we could use an independent ultrasound emitter so that the microphone array could pick it up more easily. And we could also improve on the algorithms implemented on the control modulation of the motors and acquire the same results. On this slide, we see the block diagram of our system mounted on a quadcopter. A microcontroller with the ported identification and positioning modules will send a signal to the main control piloting the quadcopter. If it detects the fellow quadcopter within its proximity, so that the UAV controller would perform its necessary actions to avoid the collision. Finally, the diagram depicts the intercommunication between two different UAVs, one emitting the sound and the other detecting the signal. So
Last night.
this concludes our presentation. Thank you for listening, and we now open the floor to any questions.
Questions?
Do you have any statistics on false detections or how many detections per trial?
Well, we haven't actually measured statistics, but what I can tell you is the program doesn't take into account anything that doesn't give a valid result, and it seems to give a valid result about 75 to 80% of the time, which is, it updates about once every 25th of a second, so we still get pretty good resolution with that.
Do you have any sense about time? That is, what's the sort of avoidance zone? If you could get your whole system onto a quadcopter, how much computing time would it take, and what does that mean in terms of effective avoidance? It's no good to know that it's coming after you, but it's going to be playing.
Right. Well, obviously, the faster the better. We would get the best microcontroller that we could afford, and hope that it was fast enough. That the computing time on our actual computer is a fraction of a second. It happens within about, again, a 25th of a second, but that's on a modern desktop, so we would have to figure out how that would work on a microcontroller.
One more.
Can I ask two?
You can ask two.
First question, just in general, do you expect any issues with constantly stability and whatnot of the system when you modulate the pulses constantly? You're going to complicate your control system for the clock.
Can you say it again?
So do you expect any stability or control issues as you're constantly modulating the pulses for the motors?
It shouldn't present any problems. Maybe our customer can answer better. He knows the hardware a little better than we do.
It is actually a concern that we are modulating the different frequencies. So this is the driver frequency. That's right. But ultimately, the speed at which you've got several timers on an RC motor, you can get these things running. You get 5 times amplitude of reverse. So we are so far beyond that. That while it's a problem on the programming level to make sure that all the ADCs stay the same, it's realistically not a problem on the control side to make sure that the motor is reverse.
Thanks, Ken.
The second question is really, I may be screwing up my physics here, but is there any concern with if you're using a frequency shift, kind of a Doppler effect as you're moving, the copter are moving towards the wave?
Actually, yeah, we had to take that into account. There's a maximum potential of about a 7% Doppler shift, just determined by the maximum speed of two incoming UAVs. So the solution to that is just to use wider filters, wider bandpass filters, so that we don't have to. So that doesn't matter, basically.
Okay.
All right, thank you.
Well. We'd also like to thank Ken for an awesome project, for giving us a lot of help, so thanks.